All right. So we've got a Yahoo firing a rocket, a rifle, not a rocket. So they could do that too, I suppose. Straight up into the air. You don't want to be this person. It's very dangerous for them, you and other people. The velocity of the bullet as it leaves the rifle is 715 meters per second. And so we're talking about a pretty powerful rifle. And the bullet has a mass of 8 grams. Okay, so that's the one little wiggle in terms of units. You'll have to convert that to kilograms for any calculations. But first, in part A, all we're asked to do is draw a free body diagram of the bullet. Once it has left the rifle and is on its way up, list the forces acting on the bullet here. I will model the bullet as a little dot. I know they're not really little BBs, but you know, I get it. So let's see, free body diagram. So we know it's moving up, but that doesn't really matter. Once it's left the rifle, though, well, there's two ways you could do this one. Personally, I would reflect reality, what I know reality to be, and say, okay, well, there's a little downward drag or rather gravitational force, in addition to probably a rather large force due to drag also acting on this thing. It's moving up, so drag acts down. Now, if you only put in gravity because you're used to neglecting drag, that's fine, okay? Not going to quibble about that one. And in B, in fact, you're told, okay, just assuming the work done by the drag force on the bullet is negligible, okay? And if we look at the forces acting on the bullet, well, that's the only non-conservative force. So that's telling us that the work done by non-conservative forces is 0, okay? And you're asked to find the maximum height to which the bullet will rise. Okay, well, if we have this condition, that tells us that mechanical energy is conserved. Yay, okay? And that means that we can say that its total initial mechanical energy is equal to its total final mechanical energy. Initially, it's moving very, very fast. And if we set the reference level of our potential energies to be there for gravity, well, then the potential energy term that normally would be involved in its mechanical energy is just going to cancel to 0 because it's 0 height above the reference level. And so all of its energy is bound up in its kinetic energy. And then finally, well, at the very top of the trajectory, we know that for an instant, right, at its maximum height, the velocity of that bullet is going to be 0. So the kinetic energy term that would normally appear on the right-hand side here is 0 in this case. A couple of other things, well, mass appears on both sides on every term, so we can cancel it out. And then all we need to do is solve for the final height, which just involves dividing both sides by g. Okay. If you plug all of that in and keep a few sig figs, you should get a final height of about 26 kilometers, okay, for its maximum height. All right, so that probably seems well, maybe it doesn't seem unreasonable to you because who has done the experiment, right, that is involved here, okay, but that's a long way. That could essentially mean that the bullet would hit any aircraft that we would have except things in orbit and whatnot. I mean, that's most of the way to sort of the line. Well, it's a good portion of the way to the line delineating the atmosphere from outer space, which is up around 100 kilometers off the ground. So that seems maybe a little unreasonable. And the reason it's unreasonable is because when you're moving at 715 meters per second, it doesn't matter how small you are, and bullets are small, you're still going to have a significant force of gravity, but also force due to drag acting on you. So in C, we add a little bit of reality, okay? So we're saying in C that, okay, the final height that you observe is actually just 3,000 meters. How much work is done by drag on the bullet from where it leaves the rifle to its maximum height? So again, drag is the only non-conservative force doing work on the bullet once it's left the rifle. And so we know that the work done by non-conservative forces is just going to be the work done by drag. Okay. And we can use the work energy theorem to solve for that work done by drag. the non-conservative work. So we know that, for instance, the final kinetic energy is still 0. It's at the top of the trajectory. And then we subtract off, right, delta KE, so final minus initial. We get that. And then delta PE, so its initial potential energy is 0, because it's still starting at that reference level, but its final potential energy is relatively large. So let me just write in that. Okay. So here's where the mass of the bullet comes in, right? We need that in this calculation. And everything else, though, we know that it has an initial velocity, magnitude of velocity is 715 meters per second. We know that it has 8 grams of mass. Remember that converts to this many kilograms, right? 3 decimal places. And if you plug everything in there, you should get that the work done by drag is negative, very important negative sign, 1,810 joules. We know that it's negative because it's removing energy from the bullet, right? If it didn't remove energy, well, it would go to 26,100 meters in the air, and it only goes to 3,000 meters. So drag must be taking energy away from the bullet, and indeed, that's what our answer here tells us. Okay, so that's that problem, and we'll move on to another one.